So we'll have 4 terms now. So 4 terms will be 1 minus e power I omega mlt minus e power minus I omega mlt plus 1. So 1 plus 1 will give us 2. Combining these two, taking minus sign out, so that will give us this term. Okay, multiply and divide by 2 will give you this expression. Instead of this, we can write cos omega mlt. So we know cos omega mlt is given by this expression. Now we can pull 2 out. So that will give us 2 1 minus cos omega mlt. 1 minus cos omega mlt is nothing but 2 sin square omega mlt by 2. So we can write this as 4. So this is the final expression for adiabatic approximation. Okay, so final expression for transition probability. So this is the final expression for transition probability using adiabatic approximation. Okay, so the adiabatic approximation is valid only when the time change in the energy of the perturbation during one period of oscillation is very small. So this is valid when the period of oscillation is very small, because it's a small variation compared with the energy difference Em minus En between the initial and final state. So this condition should be satisfied for the adiabatic condition. Okay, this should be very small. So we have considered this is very small. Okay, and this must be larger. So using this condition, we are going to have this factor sin squared omega mlt by 2, which is very small. This factor is very small compared to that of the transition probability. So transition probability is which is very small to this factor. Okay, I repeat. See here we have this factor is very small. If this is very small, this must be very small. I repeat. So this is adiabatic approximation. This condition should be satisfied, and this is very small. If this is very small, this phase factor should be very small. So whole thing is very small. We can say the transition probability is very small. So transition probability is almost 0. We can consider that the dH by d2 tends to 0. So we can say that this perturbing field is constant. So in adiabatic approximation, this perturbing field is constant. Is it okay? In adiabatic approximation, this term is slowly varying potential. It's very small. So we can say that this one is almost constant. Okay, it's constant. So no transition occurs when perturbation is turned on or off adiabatically. At t equal to 0, we have the eigenvalue equation. At t equal to t, we have the eigenvalue equation. At t equal to 0, there will be no perturbation. When time starts, there will be perturbation, external perturbation. So that's why H is replaced with perturbing field. So this is unperturbed term, this is perturbed term. So eigenvalue equation changes exactly like this. Equation 7.118. So in this case, if H of t is not weak or small, then we can use the adiabatic approximation, but no longer with the time dependent perturbation set. So this is the end of adiabatic approximation. Okay. Now we will go for sudden approximation. So now we are going to switch on and off suddenly, abruptly, rapidly, and we are going to get the condition for transition probability, how it changes in the transition probability with respect to time, and what we call this as sudden approximation. Okay, the sudden approximation is used when the change in Hamiltonian occupies a very short but finite interval of time. Here the perturbing field is very small but is switched on and off rapidly. So we are going to switch on and off suddenly. Hence the wave function will not change that much. So wave function will be in the ground state itself. Can you remember the figure which we discussed earlier? Okay. So let us assume that at time t equal to 0, then the Hamiltonian suddenly changes from h0 to h1 and remains constant. Wave function remains constant, so h0 and h1 also will remain constant. If the system is initially in an eigenstate m, we are going to consider. We are going to consider the transition takes place from mth state to m state of h0 to the first L state of h1. So m state is your ground state and L state is the excited state, and this will be your h0 and the excited state will be your h1. Okay, so this is your transition probability. The transition probability is given by initial state and the final state. It's the overlapping term, square of the overlapping term. Initial state, this will be your final state. Initial wave function, this will be your final wave function. The square of, mod square of, that will be your transition probability. Sudden approximation is valid only for the transition between discrete states. So consider a system which is subject to a perturbation, external field that is very small and switched on suddenly. We know that first order transition probability from time dependent perturbation theory is given by, we know already this expression earlier. So as I said that we are going to keep one term as constant, we are going to change another one. Now we are going to change reversely. Okay, we will see. Consider a system which is subject to a perturbation which is small and switches on suddenly. Then the term e power I omega mlt does not change. Now we are going to keep this term as constant. We are going to change this term. Okay, we are going to change this term. Earlier we changed this term. Can you remember in adiabatic approximation we changed this term. Okay, we have kept this term constant. Now we are going to change this term. We are going to keep this term as constant. Just opposite. So this will not change when the perturbing field changes suddenly. So this will become constant. So I have pulled out. So this will be your e power I omega mlt divided by h bar omega. We are going to integrate only perturbing field term alone. Rate of change of perturbing field term alone. So equation 7.121 can be written as exactly like this. So squaring will give you 1 divided by h bar squared omega squared ml and this term squared, and we are going to do you are going to integrate this term. So we have now e power I omega ml squared. Okay, e power I omega ml whole square. This can be expanded. First we will expand this one. So this can be expanded. So e power I omega ml. This is not fi. This is ml. Okay, this can be written exactly like this. This is a complex conjugate. So I have written a complex conjugate. Multiplying complex conjugate will give you answer as 1. So this term will become 1. Okay. So as I said, this is not fi. This is ml. So now substitute in that expression. Substitute the value of this one in this expression. We will have 1 divided by h bar squared omega squared ml and this term. So this is the final expression for transition probability for sudden approximation. So this is the expression. So 7.120 also 7.120 earlier. This also expresses same expression. This also expresses the transition probability. The change in the Hamiltonian h minus h naught may be large, but equation 7.123 gives only approximate result derived from first order perturbation theory, but h minus h naught is very small yet but suddenly. So now we will solve one problem. Okay, a particle is initially at t very less than 0 in the ground state of an infinite one-dimensional potential well with walls x equal to 0 and x equal to L. So we have a one-dimensional wall. The size is 0 and L. If the wall at x equal to L is moved slowly to x equals 8L. See, we are going to move the wall slowly from initial position L to 8L. First section. And in the second section, we are going to move fast. Okay, in the first section, we are going to move slowly. Find the energy, we are going to find out the energy and wave function of the particle in the new well. Calculate the work done in both the process. I repeat, this is for adiabatic and this is for sudden approximation. Okay, in both the cases, we are going to find out the energy and wave function of the particle in the new well. Calculate the work done. We are going to find out the work done. Okay. So here this is for adiabatic and this is for sudden. Now for the wall, it's given as okay. It's given as, we know that En equals n squared pi squared h bar squared divided by 2m L squared. So we know this expression very well. For the infinite quantum well, the eigen energy value is given by this and the corresponding wave function is given by this. So we know already, we have studied already in quantum mechanics 1 itself. Okay, we know already. Now for the first one, when the wall is moved slowly, okay, adiabatically. So adiabatic theorem dictates that the particle will be found at time t in the ground state of new potential well with the wall at x equal to 0 and x equal to 8L. So 0 and 8L. So now it has become from L to 8L. Okay, so 8L it becomes, for the ground state, we have n squared, which is nothing but your 1 squared, pi squared, h bar squared divided by 2m. Instead of L squared, you are going to substitute 8L whole square. Is it okay? Here it is L squared. Now we have moved to 8L. So this becomes 8L whole square. So 8L whole square, 8 multiplied by 8 will give you 64. 64 multiplied by 2 will give you 128. So this expression becomes exactly like this. So energy expression is given by this. Whereas the wave function, look at the wave function. This becomes root of 2 by L sine pi x by, the earlier it was L. Now it is 8L. So x lies between 0 and L. Okay. So this becomes root of 2L sine pi x by 8L. So now work done is change in energy. Okay, work done we are going to calculate. Work needed to move the ball, which is nothing but del E, change in energy, E1 minus E1 of t. So E1 is the previous one. So E1 minus the second one, later one, which is nothing but your pi squared h bar squared divided by 128 ml squared. Now just take the LCM. We will have 128, here 128, okay, minus 2, that will give you 126, divided by 2 will give you 63. So 63 pi squared h bar squared divided by 128 ml squared. Is it okay? You are going to take the LCM. So 2 multiplied by 128, here 128 minus 2, 126, divided by 2 will give you 63. So 63 pi squared h bar squared divided by 128 ml squared. So your del E will be this one, change in energy, which is nothing but your work done. Okay, so that is for, this is for adiabatic approximation. Okay, adiabatic approximation. And second one is we are going to move the ball rapidly, very fast. Then the particle will be found instantly at t greater than or equal to 0 in the new potential well. Its energy and wave functions are given by this. Now look at the energy expression for energy. This is as usual, we have 1 squared pi squared h bar squared divided by 2m 8L whole square will become exactly like this. The wave function will change into exactly like this. Look at the previous wave function, 2 by L. Here it changes, but here it is root of 2 divided by 8L sine pi x by 8L when x lies between 0 and 8L. Okay, so very important thing. Look at the change. This is for the adiabatic and this is for the sudden approximation. Look at the change. Now again we are going to find out the transition probability. So we are going to calculate the transition probability. The transition probability is given by, as I said earlier, it's a overlapping term between initial and final term. So you are going to calculate. Now we are going to calculate psi 1 with the psi 1 dash. This is psi 1 prime, first one. This is for the ground state. This is for the excited state. So next state, excited state, so next state. So psi 1 is this one. Psi 1 is given by this term, correct? And your psi 1 dash is given by this term. Is it okay? And multiplied by one constant should be there. You have root 2 divided by 8L multiplied by root 2 by L. So we have two terms here. Okay, so corresponding some constant should be there. Here also there must be constant. So constant is missing. So you have to write the constant. Now use this expression 2 sin A sin B equals cos A minus B minus cos A plus B will get you the answer 16 divided by 63 pi root of 4 minus 2 root. So your P11 is given by squaring, just squaring. So you have to square the term. The transition probability is nothing but square of the overlapping term. We have found out only the overlapping term. Just to square it. Just to square it will give you the transition probability. Squaring this term will give you this answer. So this is the final answer. P11. P1-1 we can say. This is for P1-1. Similarly we can calculate P11 is given by, okay, we can simplify, we will get the answer as 0.0077, which is nothing but 0.77%. Similarly we can calculate from 1 to 2 dash. Okay, so psi 1 is as it is same thing, and you have psi 2 dash will become 2n pi. Earlier it is n pi x. N is earlier as 1. So now it is 2 pi x divided by 8l. You substitute the same expression using the same formula, you will get exactly 8 divided by 15 pi whole squared. So which is nothing but your 0.1699. So you will have P21. Okay, you have P2-1 which is nothing but your 17%. Similarly, you can get the expression for P31. P31. So you have to use 3 pi x divided by 8l with the same expression and the same formula. You will get the answer as 24.2%. You will just look at it. P11 is 0.77. Your P21 is 17 and P31 will be 24. So whenever it rises, it increases, it approaches very fast. So look at the difference between these two. See here, the first one is 0.7. 0.7 is nearly 1%. And this is 17%. That one is 24%. Okay. These calculations show that particle is most likely to be found in the higher states because of the percentage, increase in percentage, higher exit. And the probability of finding the particle in the ground state is very, very small. Okay, it's very, very small. So we will stop today, and we have learned adiabatic approximation and sudden approximation in time dependent perturbation theory and a problem. Thank you, students. We'll see you in the next class.